Hello and welcome to the Ice World podcast. I'm marine biologist Nadia here with a conversation recorded during my time with the British Antarctic Survey. This episode features a chat with some of the RiPIce team, which stands for Rift Propagation for Ice Sheet Models. During December 2022, they drilled boreholes and collected data from the Larsen C Ice Shelf as part of a project to learn more about ice shelves and rift propagation, including what causes ice shelves to crack and split and sometimes create huge icebergs. I was also joined by co-host Matt Hughes as we spoke to Katie Miles, at the time working with Aberystwyth University, Sarah Thompson, representing the Australian Antarctic Programme, and Adrian Luckman, Project Principal Investigator at Swansea University.
Hello, welcome, and we're joined by the RiPIce team here today, and they're going to tell us a bit more about their project. First of all, would you all like to introduce yourselves and who you're affiliated with?
Sure. I'm Katie. I'm affiliated with Aberystwyth University and I'm a postdoctoral scientist on the project.
I'm Sarah. I work at the University of Tasmania for the Australian Antarctic Programme Partnership and I'm a project partner on this project.
And I'm Adrian Luckman from Swansea University and I'm the PI.
Well, thank you very much. Thanks for joining us. What is the project?
The whole idea is that ice sheet models don't very well capture rifting processes, so we're understanding those a bit better and improving models to include them.
Okay, so your project had you flying out to the Larsen C Ice Shelf for this. Whereabouts were you on the Larsen?
So we're on the southern end of the Larsen, quite close to the mountains, just adjacent to the Hughes Peninsula.
So can you talk us through a little bit about your journey? So why have you chosen to study the Larsen C Ice Shelf?
Okay, well, Larsen is a good example of an ice shelf that has suture zones in it. Suture zones are areas of ice that are a bit softer and warmer, and they tend to inhibit fractures. So Larsen is good because there's lots of these suture zones. We know more about them because of previous field work, and it's very accessible from Rotherham.
What was the kind of previous field work that you did in the area?
So I've been there in 2009 and did a radar survey where we got some preliminary information about that. So we're sort of basing it on what we learned then.
Okay, and then the idea was to then come back because you had discovered through satellite imagery that there was another rift that had developed in 2009 on the Larsen C Ice Shelf.
Not quite like that. We've looked at all those rifts, and one of those rifts had given birth to iceberg A68, and that got us looking again at the different types of rifting there and why they are prevented from causing further calving events. And we realised that actually not much was known about the suture ice that prevents those rifts propagating. So we thought we would base a project on that.
Okay, so how do you develop a methodology to try and tackle that?
I guess we had a couple of different branches that we wanted to address the aims of the project through. And the two main fieldwork aims were some geophysics and some borehole work. I was more involved in the borehole work, so the aim was to drill hot water drill boreholes through the ice to get into the suture zone ice so we could learn more about the ice properties down there. And I'll let one of the others talk about the geophysics.
The whole thing is really to try and give us information that will help us set up the models that can then incorporate these processes into what will happen to the future of Antarctica. So, as Katie said, there's stuff in the boreholes that we can learn about the physical properties of the ice, and we can also infer stuff from surface geophysics, such as ice penetrating radar, transient electromagnetics, and seismic surveys.
Okay, and then what other parameters are you collecting to then inform these models?
So on the borehole side, firstly, just drilling the boreholes gave us interesting information, just working out where the ice starts. So the top layer is just snow that's slowly compressing, and then you get into ice, and then at 99 metres we got into the suture zone melange mess, which was interesting in itself because we thought we might hit that at 80 from the geophysics work that was done a couple of years back. Then we stuck some sensors down the borehole. So we had a down-looking camera first and took a log from that. Then we also had a camera that views around the borehole wall. So it gives us a log with depth, and that gives us a really nice log showing us the transitions from firn into ice and then into this melange. And we also put some other sensors down, including an electrical log, which will hopefully tell us about the electrical properties of the ice further away from the borehole. And finally, we put in a fibre optic cable, which measures ice temperature. So the fibre optic cable freezes into the ice over time. It took about 10 days and then settles to the surrounding temperature of the ice. And we learned a lot from that ice temperature measurement. So we had 2 different sites, one in the suture zone and one outside the suture zone, so what we think is pure glacier ice that's feeding the ice shelf. And the glacier ice was much colder than the suture zone ice.
Is that what you expected? Did you think that the glacier ice would be colder? Is that in line with your hypothesis?
Yes, I think so.
And those probes, those temperature probes, do they actually stay there if you say they're frozen into the ice?
Yes, to be able to get the background ice temperature, they do have to freeze in. Thankfully, it's a very, very small, thin cable.
So what actually is a melange?
So the melange is, and Adrian can correct me if I'm not quite right, a mixture of snow that's come in the surface of this gap between the glacier flow units, and also sort of sea ice that's frozen onto the bottom. It becomes sea ice, platelet ice, so little specks of ice that form from underneath. And with both of those things, there's a little glacier that feeds this suture zone, so there are little blocks of glacier ice, and all of that is what we imagine to be a jumbled mess, feeding the ice shelf.
So hence the name. That's really cool. What other field components did you conduct on the Larsen?
We did a lot of different geophysical techniques. So we did some radar surveys. Some of them were repeating the work or the lines that Adrian had collected in 2009 to see if we can see any changes. And we also get a lot of information about the different boundaries within the ice. So the radar signal reflects when we get a change in properties of the ice. So we get the boundaries very clearly in that. The TEM, that gives us the electrical properties, so that gives us more of the characteristics of the layers themselves rather than the boundaries.
And TEM stands for?
Transient electromagnetics.
And then we also have something called a phase-sensitive radar. And this transmits a radar signal through the whole of the ice shelf, and it gives us a reflection from the base of the ice shelf. But if we make multiple measurements at different angles, it also starts to tell us about the crystal structure and how that's aligned. And we can look again at how different the structure is in the suture zone and in the glacier ice outside the suture zone.
How different do you expect it to be?
I think it will be quite different. I think we might be able to identify blocks of glacier ice, but then where we have this mixture of marine ice and snow falling on top, I think the structure will be really quite different. And that means that it performs differently under strain, which is why it's halting these rifts that are coming towards the suture zone.
So for these experiments that you're doing, there's quite a lot of equipment you guys are using and setting up, and got the impression it takes a very, very long time to get all of these sites set up for the measurements. How long does it take to get some of these measurements?
We got faster as we went. The first borehole took us maybe a week from just getting everything onto the ice, setting it all up as we needed it located, and then melting around 10 tons of snow. To then drilling the borehole and then logging the borehole. By the time we got to our third borehole at the second site, I think we did it all in 3 days with another day or two moving. So we certainly got more efficient as we went.
The time-consuming part of that is really just the melting the snow.
And to keep that water heated as well. So how do you ensure that it doesn't freeze?
Well, once it's above zero, it's got so much heat capacity that actually it would take an awful long time to then refreeze. We've got freezing layers on the surface. The surface of the tank was always covered in ice when we came back to it the next morning. But it would take a lot longer than that to freeze the whole thing through. So we were confident we wouldn't lose it that way.
So you contain all the volume of heated water together. Like, what storage capacity do you have? Is that a kind of fast tank?
It's a rubber tank, sometimes referred to as a blubber, and it's sort of expanding rubber tank that we fill up that has a capacity of 10,000 litres. So
Reminds me of like a garden swimming pool, like a small sort of, a big paddling pool, a small swimming pool.
Did you swim in it?
Yes. Although we swam in it when it was ice cold, everybody else got a warm bath. Yeah.
Well, yeah, I suppose. So how do you actually use this heated water? How do you drill a borehole?
Sure. So once we've got the tank full of water and we're ready to go, it's fed through what are effectively two converted car pressure washers. So they heat the water to maybe about 70, 80 degrees. And then it's fed through some hosing, and we pressurise it with a little nozzle on the end. So we used both a pencil jet, so we drilled a straight borehole, and a cone jet, which made a wider borehole because it sprayed out the jet. And the size of the opening on those nozzles controls the pressure. And then we just hang that stem and the hose on a tripod and lower it slowly, and it melts a hole as it goes.
How long does it take to melt a borehole, and how deep on average are your boreholes? You drilled 3.
We drilled 3. 2 were to 120 metres and the third was to 160 metres, and all of them took about 4 hours of drilling down because we used different nozzles. So the last one was drilled quicker than the others. But it also took about 2 hours to pull the hose all back up. So they were long days, our drilling days.
Is there a risk that the hose could then get frozen on the way up?
There is, and we were a bit worried about that when we didn't know how cold the ice was. But because we still feed hot pressurised water through when we're drilling, pulling the hose back up, then we try and minimise that risk that way. So there's still hot water being fed into the borehole.
And hence why you need so much water.
Yeah.
And then this camera data, how do you then interpret that? How are you going to analyse data from a camera?
Sure. So the video, I'm not too sure. At the moment, it's just really fun to watch. But there are definitely some interesting features that, because we know the depth of the video, we'll be able to match it to some of the other logs. So it might be really useful to compare them. The Televiewer round borehole camera gives a really lovely log that shows snow and ice layers alternating through the borehole. So that will be looking for those layers, and particularly if those layers dip off horizontal, that can tell us about the past structure and movement of the glaciers that are feeding the ice shelf. So that's what we'll be looking for from the Televiewer logs.
And can you describe to us the kind of camp setting that you have and the assistants that you have with you that allow you to work in a heavily crevassed area?
So there were 5 scientists in all, and we were assigned 2 field guides to help us. That required 3 sleeping tents, 2 people to one, 2 to another, and 3 to the third. And then we had a 4th tent, which was for cooking and that sort of thing.
Cool. So the 2 field guides help you move your equipment around, and do they help choose the most suitable site, or do you have that information already from GPS data?
Yeah, we chose the site and we chose where we were going to do the geophysical surveys, but they were there to make sure that those sites were safe and that we were properly prepared for any travel around between different locations.
And so you had another site as well that you went to for a while. How far away was that secondary site?
It was 80 kilometres away.
And that was all on Skidoo?
It was, yeah. Yeah, so 2 of us went down at the beginning to set out some instruments close to the tip of the rift that we were interested in. And then we went and did the journey again at the end to collect all the instruments in. So hopefully we'll get some really good data from that. And the instruments that we put out are seismometers, similar to the kind of thing that people use to look for earthquakes. But the ice cracking can be picked up by these small seismometers that we put out. So we should be able to pick up any changes in the rift tip and any fracturing that was going on with those instruments.
Can you calculate rates of fracturing from seismometer data? Or will it just more tell you if it's cracking and if it's continuing to fracture?
Yeah, the rift that we're studying is, according to the satellite data, still opening in a lateral sense, but it's not progressing any further because of the nature of the suture zone ice holding it up. But we don't really understand by what process it is inhibiting this rift growth, this widening of the rift, but no further lengthening of the rift. It looks like the rift is just stopped as it reaches the suture zone, but below the surface, it could be a long way away from there. It could be well into the suture zone. You just don't know.
What kind of recreation do you do whilst living on a camp for 4 weeks, 4.5 weeks?
Yeah, 4 weeks are there.
4 weeks.
Digging the snow was a large part of physical exercise. I'm not sure it counts as recreation. We had some skis in the half units, so some of us went out and did some skiing on some days when the weather was nice.
Yeah.
We did some cooking one day. We made
did.
some Welsh cakes in the
Baking.
clam tent.
Yeah, there were lots of cakes and
Impressive.
pancakes made. Yeah.
Crosswords sent via Iridium. They're pretty
yeah.
good. team
Yeah.
building exercise.
How do you actually end up doing them? Because you just get like a text PDF version on a little tablet, right?
This is down to Katie, really.
Half my field notebook is grids of crosswords.
So you just jot them all down and
I just
scribble
drew
in
out
there.
a 13 by 13 grid. I got better at the size of the grid as time went on.
What kind of food did you guys eat in the field, and how did you plan those provisions?
So we were expecting to have man food for nearly the whole time, and we did eat a fair amount of man food, so dried, dehydrated individual meals that you add water, but the kitchen at Rotherham sent us off with a whole load of vac-packed meals as well, which were an absolute godsend and made food in camp so much nicer.
Nice.
We probably had vac-pack 50% of the time in the evenings.
That was really good.
But I have a couple of dietary requirements as well, so it was a little bit harder for me because I couldn't have the standard man food or the backpacks. So I had a special set of backpacks from Rotherham, but I'd pre-planned with Bass because I knew I wouldn't be able to have a lot of the man food. And they were great at helping me find what I could have and sending me stuff to test before I came. So I had maybe 2 types of dehydrated curries that I could have in the evenings, and then a lot of sort of powdered meal replacement to make milkshakes effectively.
Wow. Is that an obstacle that you encountered in the past, having quite restricted dietary requirements during field work, especially in one of the most isolated places?
Yeah, it's something that's always a concern when I'm preparing for field work. Previously, I've been quite a few times to Nepal, and I had no idea how the food would be there. Thankfully, it was perfect. It was rice, lentils, and curries without very many vegetables because we were so high up in the mountains. So thankfully, that worked out really well, but it did make me think for the future that I needed to be a bit more prepared, which was why for this one, knowing that I'd be in the middle of nowhere, we thought about it quite early on this year.
Could
The
you make
kitchen
special ones?
sent us off with a
No
5
way.
kilo tub of gluten-free flour, and then one of the flights we had in to swap field guides, they sent some vegan butter. So we did manage free-from Welsh cakes as well as real Welsh cakes.
That's impressive. Wow. And in terms of all your science equipment and cargo and logistics, how far in advance from the start of your project do you have to start thinking about that when you're back at your institutes?
Well, more than a year, really. We've been planning this project for many years. From the point at which we're writing the proposal, we know what field equipment we're going to get from our own institutes and what we're going to have to get in from outside, and then preparing that in the background. But we have to really all get it ready about 6 months before the field work to get it shipped out here.
And then that all arrives on the Dash 7 aircraft. And then you then need to take all this cargo, check that it works here at Rotherham, and then put it onto subsequent flights.
Can you guys remember the number of
On the
twin
Aberystwyth
otters
side,
we needed?
Eight.
eight
eight
twin
We
otter
had
flights.
8 rotations to get
Which
us and our equipment.
isn't too bad because like Larsen C is only just over the other side of the peninsula, right? So it's a quick flight.
I mean, we had 8 rotations, but that did include all of our food, all of our tents, field equipment,
And us.
4
Snow
skidoos, sledges, everything was in those.
And you showed us some drone footage yesterday, Adrian, of some interesting features that were observed on some satellite imagery from back in 2002, I think. Or was it older than that?
Well, the satellite data is very recent, and these things have been known about for a long time. But they're holes in the ice shelf that people don't really quite understand how they form or how they remain open, because they're big holes, 10, 20, 30 metres across and maybe 30 metres deep. So it's a puzzle how they're still there. They're advected with the ice, so they flow with the ice, and they occur in certain locations, but actually very close to where we were camping, and actually more densely elsewhere on the ice shelf. So they're very interesting features that, in fact, were written about 20 years ago in a paper where the authors of that paper seem to think they were linked in some way right the way down through the full depth of the ice shelf to the ocean below.
And you guys actually got to go up and have a closer look at them.
We did. fortunately, because we had finished most of our own geophysical exploration, we had very good weather, and our field guides were kind enough to put their time and effort, expertise into taking us across there. We had an opportunity to go to one of these holes, which was only just over 1 kilometre from the camp, and have a chance to look into it and then go down into it.
What was that like?
It was very exciting. It was a lovely day, and it was my birthday, which was made it even more special.
It was great. It was my first experience of ice climbing and abseiling, and it was just a great opportunity. And we did some science as well.
What kind of assumption did they use to say that the dough lines were connected to the base of the ice sheet? And how do you know that they're actually not? Because that's kind of the conclusion you drew from it, right?
Yes. They had very little data to go on, because in those days there wasn't much high-resolution satellite imagery. They didn't do any geophysical or in-situ exploration of these things. They were just assuming it from some satellite imagery and just making assumptions about how these things must have formed and what they must be doing. We've obviously been up much closer, and we've looked into there, and we have the benefit of having boreholes nearby where we can see the layers of the ice. So we're pretty convinced that the base of the holes is at the same level as the level in our own boreholes, where we can see that the ice becomes impermeable. So it's just simply that same layer that the holes get down to.
What do you think the greatest challenges that you've encountered whilst being on your fieldwork?
Well, we had a very small Scott tent, and getting into your sleeping bag in a tiny Scott tent, every night it just got harder and harder and harder.
Not a pyramid tent?
It was a pyramid tent.
A Scott
But it seemed to be a Scott pyramid tent.
Oh, right.
But it seemed to be an extra small one. And I'm not a huge bloke, but it was a real struggle inside that tent.
It became known as the kids' tent.
I did start having trouble getting in and out of the toilet tent because we had such nice weather that it melted out, and so I had to keep shoveling to flatten it out. And by the end, I had to literally pull my knee out to be able to crawl out of the toilet tent.
my God.
I just couldn't get my leg high enough with the bathing boots on.
Yeah, that was a challenge.
And what next?
Next for me is starting to look at some of the data along with the rest of the group, and trying to work out what we found, and hopefully getting some papers from our results and going to conferences and sharing that knowledge.
We're also going to use the drone footage for outreach purposes, so Time for Geography. It's an organisation that make videos for schools. We'll be using our drone footage to make an educational video about
Awesome.
Antarctic fieldwork.
Well, I have to go back to Tasmania and back to my regular job. And I work a lot with the Australian programme out there. So I have fieldwork coming up in New Zealand that is looking at detecting crevasses using a radar, a similar system to the one we used on Larsen, but it's mounted on a helicopter. And then I've also got fieldwork for next season, which will be in East Antarctica, using a lot of similar methods, but on different ice shelves.
Well, thank you very much for your time.
And thanks for sharing your project with us. It's been really interesting to follow through the season, and glad it's all gone well.
Thank you very much.
Yeah, safe journey back home.
Thank you.
Thanks. Katie is now working at Lancaster University and has been to Antarctica twice more since the episode was recorded back in 2022 in the Little Library of Rotherham. Her and her team have been studying ice shelves all around the continent. In the 2023-2024 season, Katie joined Sarah to go back to the Shackleton Ice Shelf in East Antarctica as part of the Australian Research Project. And at the time of recording in February 2025, that is where Sarah is right now. Katie has also just come back from an Antarctic season on the McMurdo Ice Shelf in West Antarctica with the New Zealand team, both very busy scientists. Their work continues looking at ice shelf properties and stability through hot water drilling techniques and borehole measurements, whilst Adrian is leading the publication of 3 other papers from the RiPIce project, which have actually spanned further work on the Ross Ice Shelf. As always, if you're thinking of a new challenge, take a look at the jobs section on the British Antarctic Survey's website. You never know what roles might suit you, and the experience of working in Antarctica can be life-changing. If you enjoy the Ice World podcast, please keep following and sharing. Maybe even write a review for your favourite episode. It really does just help us get the word out. Coming up, we'll hear from the doctors of Antarctica, not the PhD doctors this time, but the medical ones. Tune in next time to hear 2 discussions between an Antarctic doctor at sea and an Antarctic doctor on station. I'm Nadia Frontier, and thank you for listening. See you next time.